The recording again. Okay. Okay, so somebody was asking about the excitons. So I'll tell you what they are, but we have to start back from where we left. It's just few slides. I'll tell you what the excitons are. So if you have, let's say, a conduction band, and if you have a valence band here in a semiconductor, and how these bands are formed, I told you the half story of how the bands are formed in the E versus K space. You get something like this on both of the sides. You actually fold these bands back to get the EK. That's what I'll be talking about in upcoming slides, but this is energy versus space. Okay, this is a different thing. This is energy versus K. That's why this is called as band diagram. Oh, sorry, this is called as band structure, and this is called as band diagram. I always try to emphasize this point because people are always confused about it. These are two different things. And what I want to explain is that if you have, let's say some energy level here. Let's say this is donor energy level, and usually the difference between these two is much small. Let's say EC minus ED is approximately of the order of KT or few KTs, where KT is the room temperature equivalent, thermal equivalent of temperature, that is 0.0256 electron volts. Okay, now what happens is that if there are electrons here, there is empty states present here. Okay, now if the photon comes in here with certain h omega energy, and it can excite electrons from this region to this region, or even if there is certain temperature which is T is non-zero temperature, you can get electrons. Because electrons are present in the donor level because of the doping, you get electrons here, you get electrons here, and what is left behind is a hole. You have hole here, you have electron here. Now because there is a very, I should say, these are electrostatically attractive towards each other because of the opposite charges. Okay, electrostatic Coulomb attraction is there. So this whole entity behaves as a single entity only, not as two charges. So this is something called as
When
exciton.
they can recombine, sir? Like, what's the reason
Right.
for stopping
Yes.
recombination?
Yes, they can recombine, but there are certain conditions in which these excitons get formed. They are not a day-to-day thing in semiconductors. They don't always get formed. There are certain well-defined conditions when an exciton can form, and those excitons are stable in that particular system. They don't recombine back. Yes, you are correct. They can recombine. But here we are assuming that that particular recombination time is much, much greater. Okay, they are definitely going to recombine in the end, but we are
Oh,
taking them as a single entity here. Okay, so they move as a single entity. It is just like a it's just like something called a pseudo hydrogen species. Why pseudo? Why hydrogen? Because it is just like a positive charge and an electron, just like the hydrogen atom. That's it. So what you do, you can model this thing as an hydrogen atom, and that's what is done quantum mechanically. If you have an exciton, you can model it like a hydrogen atom, and it is as if you are applying all of the electric field and other things on a hydrogen atom, and you have to solve the Schrodinger equation and other things for the hydrogen atom. So that's why it's called a pseudo hydrogen species. But the important thing for it is that this particular energy difference between the electron and the hole should be much very very small. Otherwise, excitons will not get formed. Otherwise, what you said, if let's say you have a hole created here, you have an electron here. This is conduction band, this is valence band. But you can also call this as exciton. Okay. But there is a higher chance that this may recombine back and they will annihilate. Okay, they will give rise to a photon. So there are certain conditions only when the exciton gets formed, and it's a very I should say you have to dig a little bit of deeper to understand when the exciton gets formed. It's not a day-to-day thing in semiconductors. Okay, So let's move
Okay,
back
sir.
to,
What is one condition which actually stopping them to recombine? Like any
yeah, that is I don't want to go into that depth. It's going to take a lot of time. You know that it most of the time depends upon the epsilon of a material. You know what the epsilon is?
permittivity?
Exactly. So you know the force of, because this is a positive charge, this is a negative charge, this is an exciton, this is a hole actually, and this is an electron. The force of attraction given by the Coulomb's law is k q1 q2 by r square. And you know this k is 1 over 4 pi epsilon q1 q2 by r square. Let's say this is the distance r. And and you see that these all things are almost like let's treat them almost like a constant. Maybe you, because charges are constant, they are not going to change. And the distance between these two excitons, let's assume that that's also not going to change. They are spatially at a similar distance. Or okay. Now, what is the thing you can play with, or what is the thing you have in the material? 4 and pi is constant. You have the epsilon in the material. And epsilon denotes the response of those charges to the external electric field. And that is the fundamental thing. People play with these epsilon permittivity in order to play with these excitons. Okay, so you make different regions of the semiconductors, like you have some material, you make certain you make a device with different material stacked over one another. Let's say you have one material, you have other material, and you have some other material here. So this is having epsilon 1, this is epsilon 2, this is epsilon 3. And because of the different band diagram of of this particular device, you get totally different energy levels as well as the inbuilt potential inside the device. You get, let's say, energy level something like this. This is an exaggeration. You get something like maybe this, and maybe this. Okay, where okay, so this is like maybe this thing, or like this, not drawing to the scale. Okay, not this thing. So this is the band diagram, what it may look like for when you combine different materials over one another. Okay, so then you have, let's say, this particular region where this is a different material altogether. This is a different material altogether. That's why you have a different band gap. This is different material altogether. That's why you have a different band gap. And what happens is that because they are different materials, their epsilons are also different. And epsilon determines the force of attraction between these two charges, between a hole and an electron. That means if you increase the epsilon, the force of attraction between these two charges decrease. If you reduce the epsilon, the force of attraction increases. What do you want for an exciton to stay? Do you want epsilon to be higher or lower?
Higher,
Why?
because the force of attraction is weaker.
If the
So
correct, if now the force of attraction is weaker, they will dissociate, they will separate out. They won't move as a single entity. And if the force of attraction is higher, then they are going to recombine back. There is a in between solution. There is a balance between these two. Okay, that's why I told you we play with certain lot of many things here. Okay, so but it is predominantly determined by these permittivities. So if you play with the permittivity, you play with the force of attraction between the two charges, electron and the hole, and whether they move as a single entity or whether they get separated, it depends upon this epsilon of a material. Okay,
okay, sir. Very nice explanation. Thanks.
there there
Sir,
there are, there
lastly,
are
one doubt.
okay, yeah, yeah, sure.
Whether electronic band gap, like the electronic band gap and optical band gap, both are same or like different?
No, no, no. There's a difference. There's a difference. Electronic band gap is different, and optical band gap is different. You know what happens if you have a crystal, and if you have a, let's say, you have atoms. The concept of electronic band gap and optical band gap is similar, but they are not two same things. This is an electronic crystal. Okay, just like what I was earlier defining. Just a second. I hope I'm recording all of this because I have to. Okay, sure. So this is electronic crystal. These are atoms and so on and so forth. And if you have, let's say, electron, if you impinge an electron over it, you fire an electron over it, or let's say electron is moving inside it, it will go here, here, it will go here and there. And what the EK diagram gives you, it gives you what values of energy of the electron in certain directions of K will be accepted by this crystalline structure, or what energy values of the electron will be possible in different K directions. That is what the EK diagram gives you. That's what you get as this, let's say, that's what you get, let's say, uh, you get a something like this. You get this as conduction band, and you get this, the minima of this is conduction band and maximum of this is valence band. But this is band structure of, this is the electronic band structure. Okay, it occurs because if you consider a lattice, electron is moving as a wave, just like I explained. Some waves are going here, some waves are going here. There's an interference effect, and because of interference, there are some energy values which are acceptable, some energy values which are unacceptable. That means there is a constructive interference with certain direction, there is destructive interference in certain direction. Let's say let's say electron went in this direction and it faced a destructive interference. Then it means that electron cannot have that particular energy. There is a gap. That's what this means. Now, electron, let's say, moved in this direction and it faced a constructive interference. That means that particular energy value is acceptable. Okay. Now we are particularly considering a wave picture here for the electron. Now, what is a photonic crystal? This was electronic crystal. If you have a photonic crystal, what you do, you place certain other certain other stuff here in the middle. And what is that stuff? This is certain other material. Let's say this is, let's say this particular, oops, let's say this red region, except the where I have made the circles. This is a substrate. Oops. Let's say this is a substrate. Substrate means certain some material over which some other material is grown. Let's say this is a substrate made up of sapphire. Sapphire is aluminum oxide. Let's say this is aluminum oxide base. And if you make certain regions like this, black circles here, over here, deliberately, artificially, not, I should say, naturally. Naturally, it can also happen. But let's say we make it deliberately. We make certain regions with certain periodicity. You repeat them with the distance between these two circles is a, that is the same here, and that is the same here. That means these are periodic arrangement of certain other material. And let's say this material is having a refractive index N2, and the
Like a
substrate
grain?
is, it's not a grain, it's a different material altogether. Okay.
Okay.
Let's say the substrate is having refractive index N1. This is the refractive index. And this is the refractive index of these black ones, which is a different material altogether placed in this fashion. This is the refractive index. This refractive index plays the same role as the potential in the electronic crystal, because if you have a variation in refractive index that is same that you have a variation in potential in electronic crystal here. You know that I showed you that if you have a positive charges, you get potential like profile like this, electrostatic potential profile. You get a same thing over here if you have a refractive index variation. Let's say you have a let's say this is N1, this is N2, and this is N1. Let's say you have stacked some material in the sense that outer two materials are having refractive index N1 and internal is having refractive index N2. There is a refractive index gradient formed, which looks something like this. This is the refractive index profile. Refractive index profile. Okay. And it plays the same role as that of electron in a potential well. Now you have a light in some well. That's it. When you place the light in certain region where there is a high refractive index, it will guide it. It will accept that light. Just like there were certain acceptable values for electrons in this electronic crystal. When you hit this particular photonic crystal with light, certain light in certain directions will create constructive interference. In other directions, it will create destructive interference. Overall, you get EK of for light, which may look something like this, which may look something like, let's say this is EK for photons. It may look something like this. It may look something like this. This is the same story as that of the electrons. That interference in this region is creating acceptable values of the energies of photons and unacceptable values of energies of photons. The same thing which is happening with the electrons. But here the story is with the refractive index. Here the story is with the electrostatic potentials created by the nucleus. If you see the mathematics, even that is the same. But the only difference is you solve Schrodinger equation here, and for this system you solve Maxwell's equation. And when you solve the Maxwell equation, you get something called as modes, which are the accepted electromagnetic modes, TE mode, TM mode, which can flow through this photonic crystal. And that is the entire story. You got it or
Okay.
not? Was
Yes, sir,
it
I
too
got it. Thank
complicated,
you,
or
sir. No,
I don't know whether I
you
was able to make you
explained.
understand, but
Yeah, yeah. You detailedly explain without with less mathematics and with
yeah,
more
that's what.
practical.
I don't want to directly go into maths because the maths of it is a little bit complicated. You need to solve many of the differential equations, particularly solving the Maxwell's equation with certain boundary conditions. So this is the kind of a layman explanation of why this band structure arises in photons as well as the electrons. And now this has taken a lot of time, I guess. So let me just take this stuff from here. Let me just cut it and paste it over here so that it may remain here. And where I was is uh, okay, so I was here. Okay, so what I was explaining uh, okay, so I was explaining that when you have some electrons going in this direction, electrons going in this direction, so you know from the basic maths, the waves going in this direction and in the opposite direction create something called as standing wave patterns. And that is the same thing you get in this crystal by this particular explanation, that if you consider some electrons going here, some electrons going here, you get this kind of interference effects. And what happens, you get certain regions around the nucleus where the electrons concentration rises, and certain regions between the nucleuses where the electron concentration dips. That means if you have nucleus like this of the atoms, you may get certain regions where the electron concentration will be something like this, maximum around the nucleus. And you may also get certain regions where the electron concentration will look something like this, maximum between the nucleus. Okay, so these are the two scenario. It arises because certain waves are going in this direction, some waves are going in this direction. So you may get different regions of electron concentration. That is what this particular scenario is showing. This particular plot is showing. You have a You have some regions where the maximum of the electron density is around the nucleus, but you have some regions where the maximum of the electron density is between the nucleus. Okay, and mathematically you can simply write them in terms of sine and cosine terms. Okay, so what you can do, you know that using Euler identity, e to the power I theta is cos theta plus I sine theta. You can write that in terms of this particular thing, cos of theta pi x by a plus minus I sine pi x by a. And now again, using simple maths, you get from this particular thing to this particular thing, where the psi plus represents the region where, let's say, you have maxima at the nucleus, at the atomic locations, and psi minus represents the locations where you have maxima between the two atoms. And you get the equations for these in terms of sine and cosine, a simple mathematics. Just to expand this in terms of the mathematical functions. Okay, and now you mod psi square it, you get the probability densities. That is what actually is shown here. These are the probability density shown. So one of the probability density is proportional to cos square, other is proportional to sine square. That means psi minus, which is this particular thing, red thing, the for this psi minus square is proportional to sine square pi x by a, and for the orange one, the psi plus square is proportional to cos square pi x by a. This is the simple mathematics. Now what happens after this? Now what happens is that you calculate the overall average value of the three probability distributions. Why there are three probability distributions? Because earlier there was a traveling wave of the electron which was going in this direction. These particular distributions arise because of multiple reflections. Okay. Otherwise, we earlier considered the traveling wave. So the traveling wave was going here. Certain electrons were going in this direction. Certain electrons were going in this direction. So that is how this psi minus and psi plus picture comes in this schematic. And what happens is because of different electrons localized around atoms and in between the atoms. Some electrons are localized here, some electrons are localized here. You get different potential energies for these electrons because you see that this particular electron density is directly under the influence of the atom, while this particular electron is in between the atoms. So there will be different potential energies for these two. And you see that for potential energy for the psi plus is lower than that of the traveling wave. The potential energy for the psi plus means for those who are around the nucleus, it gets lowered by certain value, while for the psi minus, it gets higher than certain value. Why it gets lowered? Because of its associated distance from the nucleus. Okay, because if because some distribution is peaking between the nucleus, while the other distribution is peaking at the location of the nucleus. So these are having two different potential energies. And when there is a difference in the potential energies, you get the difference in the potential energies given by you have the difference in the potential energies, and because of that you have the energy gap, because there is potential energy of psi minus potential energy of psi plus. There's a difference in the energies of the potential energies of these two electron waves traveling in this direction and this direction, and because of that you get energy gap. You get certain values which are not allowed, certain values which are allowed in the same crystal. That is the explanation which comes just because because of wave mechanics, just because we consider the waves. And and now what happens because of it is that, because earlier we found that for k equals to n pi by a over here, just like this, we found that k is discretized in terms of integer multiples of pi by a. So there is a gap which arises. Earlier for a free particle, the ek looks something like this, continuous. Now exactly at the positions where k is an integer multiple, k is integer multiple here, it is pi by a, this is minus pi by a. That means for these two regions n equals to 1. So at the region where k is an integer multiple of pi by a, there opens up a gap in the energy spectrum, in the energy diagram. And that is this particular gap, which is the band gap, Eg. And this particular thing reflects directly from, again, the interference. This is the same explanation I gave here. This is the same thing which comes from here. So this gap, when it opens up, it tells you that electron cannot stay in this region. Electron cannot stay in this region. It has to be in this particular zone or this zone. It cannot stay in the red zone. Okay. Now you get from this picture to this picture, because when you go higher and higher in energy, you get similar bands with certain band gaps. You go higher in energy, you get some same bands. Okay, what you do, you don't want to deal with an extended problem. Just like this, you have these accepted bands. You go higher and higher in energy. There's some band gap. As you can see, this is the band gap. This is the band gap. This is the band gap. These are band gaps. These are all band gaps. Now someone will think, and someone will just maybe ask me that why are so many band gaps in a crystal? Yes, it is correct. A crystal is having multiple band gaps. It's not only having one band gap. If you somehow excite an electron from this region to this region, you have to cross this band gap. But if you again give it some energy, you have to again cross this particular band gap. There are multiple band gaps in a same crystal. That is the notion which comes from that's the notion which comes from solving mathematics, and it has been also proved experimentally. So now what happens is that we don't want to deal with these kind of with these bands, with these particular bands, because it kind of takes a lot of space to show the schematic of it, and you don't kind of want to spread these bands in a k space. You want them to be localized. You want them to understand in a very simplistic manner. So what you do, you fold these bands in the first zone, which is this particular zone. This is something called as Brillouin zone. You fold over these bands in this first zone, and you get these particular things. Done. This particular thing comes here, this particular thing comes here, this particular thing comes here, this comes here. It gets kind of inverted when you fold. It's just like a folding of a it's just like folding of a I should say hexagonal type structure. If you fold it over one another, these particular bands will come just like this. And this particular thing now here is a gap. And this particular thing is also a gap. Okay, so now what we have done, we have simplified this particular picture to a band picture where there is a reduced zone representation, the Brillouin zone. This representation where we show the energy band diagram in a first Brillouin zone, this is called as first Brillouin zone, where there is something like this, the energy band, something like this, and there is something like this band. This is called as reduced zone representation. Okay, so now this picture goes here, the same reduced zone representation, reduced zone representation, and you get a EK diagram, the one which is shown in the books, the simplistic one. So there is a band above this also, and this bottom is called as conduction band, this top is called as valence band. This particular band has inner electrons. These are innermost electrons, and these are very tightly bound to the nucleus. And if they are tightly bound, they don't take part in conduction. Not take part in conduction. So which are the electrons of our interest are located in this particular bands? And when you let's say excite these electrons, they go to this band and they play a part in conduction. That means they accept the energy value and go to the conduction band. How do you excite these electrons? You let's say shine light or maybe apply some potential or even the temperature, and you get electrons which play part in conduction. All right, that was the entire story of these particular bands. Now what you do again when you have these particular bands, something like this, and you have the inner band. Oops, there's a gap. You have the conduction band, valence band. You have to model it somehow. I mean, we guys are obsessed with modeling it with simple systems. We knew for a free particle, the E was proportional to k square. But here it's not exactly k square because at the ends, at the edges, the parabola is kind of stretching and the curvature is changing. So you cannot model it directly as k square. But around the 0 point, you can just fit a parabola to it, just like this, approximately. And you can model this as E directly proportional to k square. That is why most of the times we write even in semiconductors that E equals to h bar square k square divided by 2m. Otherwise, this is a very simplistic region if we are only considering electrons to be in this particular region. If the electron goes in higher regions, then this parabolic approximation fails. You see that this is a fitting curve to this particular curve. As electron goes higher and higher in energy, this dashed line parabolic fit fails to match the exact band. Then we have to consider some other things. But for the
So,
at least
sir,
the
as you says, uh,
yeah.
sorry for that. So, as you says, when you fold all the uh, states, then you will
Hmm.
get only two bands, or above that also you will be having some bands.
Yeah, there are many bands above. As you go higher and higher, there are many bands. Just like this picture I showed, this is a bottom band, this is this band, this is this band, then there is other bands. Okay, this is the first Brillouin zone. There are many bands as you go higher and higher. Okay,
Oh,
so this
and
is band, this is a band, this is a band. Sorry, there is a gap between. This is a band, there is a gap, band, band, and there are as you go higher and higher, there are many bands. And this particular region is from minus pi by a to plus pi by a only. This is zero. This is the k direction, and this is energy. And that's why this particular region is called as Brillouin zone. Okay, and it's the reduced representation of this extended zone representation. And there is something this particular 0 point where the k equals to zero. It is something called as gamma point. You have many points. You have something called as X point, you have gamma point. Basically, if you have, let's say, a crystal like this, and if you consider a point here, which is at the center almost, then you compute the band structure around this point, k equals to zero, and you call this as gamma point. If you go in this direction, this is called as X point. If you go in this direction, this is called as M point, this is called as R point. So how to determine these directions? Basically, these are determined by different Miller indices. Or if you go in this direction, let's say 100 Miller indices direction, or let's say 1 bar 00 Miller indices direction. So that is what these points are basically showing you. In what Miller indices direction in the three-dimensional lattice, how will the energy of an electron look like, or what energy values will be accepted by the electron in different directions in the crystal. If electron goes in this direction, if it goes from gamma to X, there is one more zone here which will be, let's say, gamma to X. There is one more zone here which will be gamma to, let's say, gamma to M. Then you can show these bands and these will be extended. You will see some structures like this. Okay, there is, let's say, uh, I'll show you band structure of silicon. This is the actual thing you get. This is the actual band structure of the silicon. So what we have only drawn is this is only the region from L to X. That's it. This is the complicated band structure of the silicon, which shows in different directions there is different allowed values of energies of an electron. And if I okay, so if I just take a screenshot of this, or maybe just copy it, copy and paste it over. Let's paste it over here. If I paste it over here, it's, yeah, let's keep it here. So what you see, what I have drawn is only this particular thing, which is from gamma in the towards the x direction, and this is L direction is the another direction. But there is a band gap. But if you go from x direction to some sigma direction, this is one more direction in the lattice, because when you consider the three-dimensional lattice, you have Miller indices. It depends whether you are talking about this direction, this direction, this direction, or this direction. Accordingly, electrons' energy will be having different values along different directions. That is what this particular band structure tells you. If you go from gamma to X, accepted values of energies are like this. If you go from gamma to L, accepted values are energy are like this. That is the simple explanation of the band structure. You don't need to complicate anything. These are just in different directions. This particular line separates different directions. That is how the band structure is read. That's how these plots are read. So if you go from gamma to X, you go from gamma to some other distance, some other direction. These are different directions as a Miller indices. Okay, so that is that's it about the band structure. Basically, I think I explained it.
So that
Okay.
is the direction dependent band structure. It's like that, sir.
Yes,
But
exactly. This is the overall actual direction dependent band structure. Correct. You got it exactly correct. And here
thank
I initially showed from the gamma point to this is the x point here, the gamma point to x point. You can go to gamma point to, let's say, R point, which may be somewhere around this direction. Gamma point to x point is in this. If your electron moves along from this direction to this direction, its accepted values are something like this. If it moves in other direction, gamma to R, its accepted values may be somewhat like this, somewhat different. But that is what the entire band structure tells you. Is it clear?
Yes, sir. So, but if we mobilize the charge carrier by applying potential, then like
Yes.
overall the band structure will also change, and like conduction band to go
No.
electron to there.
What happens? That is this scenario I have actually shown in the next slide. But I was about to skip it. But now you have asked this question. Let me just show it. So this is the reduced zone, first Brillouin zone. So when you what happens when you just kind of consider this as a this particular these are inner electrons, these are filled, and they don't kind of play a part in conduction. These are totally filled states, and these are mostly inner s orbitals of the silicon mostly. And this particular thing here is the, let's say, the valence band minima. This is the conduction band maxima. And if you just somehow some certain electrons move from this band to this band, these particular electrons here, they play a part in conduction now because they are freely available to move. Okay, here it is as if here the electrons are so kind of so tightly together that they are not able to move at all. It's not a correct explanation, but you can understand it classically that if you have beads, if you have kind of beads on the string, and you have if you have so many beads, you cannot move those beads kind of you cannot move them at all, and they won't play a part in conduction because all of the bead is completely filled. I mean, there are so many beads over this particular line. But if you just remove some beads, let's say you take this bead out and you take the other beads out. Now you have only four beads left. Now if you just hit it with something, these are going to move. Okay. So that is what happens in the conduction process. That's what happens in the EK picture actually. You remove certain electrons in this, you pump them to the conduction band. Now, when you pump them to the conduction band, certain states become vacant in the valence band. Now, what that causes? This electron now can move here. This can move here. And there will be chances for electron the motion to move. Electron has a free will to now just move freely around this band, and it creates conduction process. That's it. That's the simplest explanation of conduction. That means if you have this band like this band like this, you created certain empty states because those electrons went here. Okay, now what happens when you apply a field, electric field, because force equals to minus q times electric field. So electron goes opposite to the direction of field. That means this electrons let's wants to go here. These are vacant states. These are something called as holes. They are just vacant states, but they move in the opposite direction. They move in the same direction to that of field. They move in this direction. Why they move in this direction? Because there are some electrons here which are actually filling these holes. So when the electron fills this hole will appear here, and it appears that as if the hole has moved in the direction of the field. So as a result, the conduction takes place. Electron moves here, hole moves here. Overall current is basically the electronic current plus the hole current. If the electron is moving this side, the current is flowing in this direction. If the hole is moving this side, current is flowing in the same direction. So the overall current flows in this direction. So that is the net result of the current. You got the point?
Yes, sir. So it's like a
So
cascade event. If we like promote one electron, like it will influence, like as you told, one bead. If we remove, and it will.
exactly. A brilliant explanation. Brilliant. I mean, you have got it. You have got the concept. You just have
Thanks.
to remove. You just have to remove one that creates hole. Other electrons now move in. It appears like as if hole has moved, but it's not actually the hole that moves. It's the electron that goes into that hole, and it appears that the hole has moved into the other region, and as a result, conduction takes place. Now, it's a very simplistic explanation. When you go to higher and higher classes of quantum mechanics, you see that there is some bizarre thing associated with these holes and electrons. But let's not go into that. This is a simplest picture, at least what you have to study till your, if you do masters or till your undergraduate, final year undergraduate courses, or even the postgraduate courses. But if you somehow go into research, then you will see that how you can see a hole as a different particle itself. But that's the basic scenario of how the conduction takes place. Okay. So this is about the conduction of
Okay.
how the conduction takes place. Now, I think, okay, this part, will I be able to finish? No, I don't think so. Okay, what has happened? So let's take first of all some of the questions. Maybe we will be able to see some of the questions, and maybe from this part I will continue in the next session because I want to complete this part. It will give you a good understanding of the density of states, the Fermi function, the number of electrons, how the conduction takes place. It will give a good representation of it. Let's pause here and let's move to the questions. Let's see what are the problems which we need to solve. These are again some basic problems because if you have understood the concept I showed you now look at this first question. It's saying that if you have a rectangular lattice where there are atoms like this and the distance between the two atoms is a, which is the lattice constant, that is similar, and you have to represent when you represent it in a K space or the reciprocal space. The various segments in a reciprocal space are referred to as Brillouin zones. What I told you, this is the first Brillouin zone. This is the reduced zone representation, and this is the first Brillouin zone. And this Brillouin zone is from minus pi by a to plus pi by a, just like we defined. This is zero. This is the K. So it is saying that which of the following is true about reciprocal space. So which of the following is true? The first Brillouin zone is from minus pi by a to pi by a, and the periodicity is 2 pi by a. That means this is the overall, I should say the width in K. If you see overall this width, this is 2 pi by a, and this particular there will be some more bands in this region which will be in different directions. It is going to repeat at this 2 pi by a. You will see this is, let's say, minus 2 pi by a to plus 2 pi by a. So the overall periodicity in K space will be 2 pi by a, and they will repeat in different directions in that periodicity. And it will be the Brillouin zone will be drawn from minus pi by a to plus pi by a, just like we showed how we got to this particular result. So that's it. And now one important thing I want to tell you that these are the atoms in real space. Real space means real space. Real space means the space we are living in, the space we feel. Okay, it is in a sense a real space. That means if you just look at the atoms, you are looking at the real space, the presentation of the atoms. If you just look at it, you will see something
Difference
like
between
this.
real space and lattice space. Lattice space is just imaginary.
Yeah, I'm just going to tell you. That's what I'm going to explain. So this is a real space, and this is the distance between the two atoms, which is a, and the overall length of this crystal is L. So this is simple. People can relate with it. Now, if you go into something called as K space or something called as Fourier space, you see a similar thing. You see a similar thing, but with a certain significant difference. Now, what has happened in reciprocal space, since it's also called as reciprocal space. I will tell you the simplest explanation of how to understand it. I won't go into the jargons of Wegener seed cell or whatever the people use in terms of the lattice structure, but I'll tell you the simplest explanation of how to understand it. When you go to a reciprocal space, in reciprocal space, everything is reciprocal of whatever it is in the real space. Reciprocal means उल्टा. So जो भी real space में था उसका उल्टा हो जाता है reciprocal space में. मतलब if the distance between the two atoms in real space was a, this a becomes now the overall this thing. And if the overall length of the crystal was L, this L becomes the spacing between these two. This is the reciprocal space. That means these length spaces kind of interchange or reciprocate with each other now in the reciprocal space. And why does that happen? You know that you have time, you have frequency. A simple Fourier transform you have been kind of taught about. If you have certain some time value, you can just convert using Fourier transform to a frequency value f. That frequency is 1 by time. Or if you have angular frequency, that is 2 pi by time. Basically 2 pi nu, 2 pi frequency, that is 2 pi by time, 2 pi by t. And it tells you that what components are repeating in time with what frequency. It just tells you about that. Now it turns out this is one Fourier transform. There is another Fourier transform called K-space Fourier transform. If you are in X space, real space, you can Fourier transform it, something called a spatial Fourier transform, and you get into a K space. That means X का जो एनालॉग है, X का जो बड़ी है, that is wavelength. You define wavelength in terms of space coordinate. That means if you spatially transform the wavelength, you get something called as k value, which is 2 pi by lambda. It is similar to that of this. But this is in space, this is in time. That is the whole fundamental thing about the reciprocal space and the reciprocal Joby lattice and other things. You have to go to some different space. Now, why do you have to go? That is a different story. Just like you get some more information in the frequency domain when you convert a time domain signal to a frequency domain signal. That particular information is not available if you just look at the time domain signal. If you have just a time domain signal like this, if you convert into a frequency domain signal, you see that there are certain frequency components repeating at certain frequencies, omega 1, omega 2, omega 3. It is the same thing if you have some form which is repeating in space x. You Fourier transform it in space, that means K Fourier transform or spatial Fourier transform. You get something like this. It will show you something repeating in something with some repetition k1, k2, and k3 and k4 and so on. That is it. You don't have to kind of think much more about it. Now the actual representation that comes because of the how the crystal is actually how the depends upon the crystal structure and other things, but that detail I will try to omit because it is a kind of, I should say, tough beginner. It's very difficult to understand in the three-dimensional representation. But that is the
Sir, this
importance of
transform we will perform because to find some periodic resolving kind of thing.
exactly. That is why this is very important in crystalline materials. Because in crystalline materials, atoms are periodic. Whenever you have something periodic, just close your eyes, think about Fourier transform. And think about Fourier transform. If you are dealing with time, think about Fourier transform in frequency, time to frequency. If you are dealing with space, if something is repeating in space, you can Fourier transform it to K space. That's it. That is the end of the story. And this
Sir, like
particular,
that ultrasound
yeah.
ultrasonography, sir.
Ultrasonography uses the same Fourier transform in K space. Not only ultrasonography, the radar,
And
the
sir, ECG.
hmm, most of the imaging techniques basically use K space Fourier transform. If you have if you have certain waveforms in the space, you want to you want to see or reconstruct the image where those waves are coming from, you can get it from the K-space Fourier transform. That's a different story, but just to make you guys understand this thing. Okay, this was the first problem. Now this okay, do you have any question?
No, sir.
Okay, sure. So just moving to the second question quickly because I think I'm overshooting the time, but that's fine. But let's move to the second question quickly. We have to consider an intrinsic silicon. Intrinsic silicon means there is the conduction band, the valence band, and intrinsic level is in the middle. That means this is the Fermi level. It's exactly in the middle. and this is the 1.12 electron volt band gap, and the probability that a state located at the bottom of the conduction band is the probability that a state located at the bottom of the conduction band is filled be FC, and the probability that a state located at the top is filled with which of the following is true. Okay, so what he is saying that there is a probability that this state will be empty is given by FV, and there is a probability that this state will be filled, it's given by FC. So which of the following is true about these two probabilities? Now, what
Both will
happens
be equal in intrinsic
exactly? Why they will be equal? The question is
because
why.
the Fermi level lies exactly half of the band gap position.
Hmm. What will happen because of that?
Then the energy difference between Fermi level of the top of conduction band and bottom of the bottom of the conduction band and top of the valence band will be exactly same.
Correct. Correct. Another simplistic this is a correct explanation, but a simplistic explanation will be the number of electrons created here will be equal to the number of holes here. If there are two electrons here, that means they have come from somewhere here. If we're talking about pure intrinsic semiconductor, that means the probability of these being empty is equivalent to the probability of these being filled, because they are definitely coming from here. So if there are, let's say, two holes, there will be two electrons here. Two holes, two electrons. And your explanation that Fermi level is exactly in the middle, so this thing is exactly equivalent to this thing. So that's why the overall probabilities will be equal in both of the cases. It is as if you have two states. If you have, let's say, if you have this electron filled with electron and this is a hole, and if this is F represents the probability of being filled, then 1 minus F represents the probability of being empty. This is the filled, because the sum of probabilities should be equal to 1. That means F plus 1 minus F should be 1. That means 1 is 1. That means the overall probability is 1. The overall total probability. Okay, you got it. That's the simplest explanation. If you kind of understood this. This is a very simple question. And now if you move to the question number 3, now you have to consider an intrinsic semiconductor again, where the Fermi level lies exactly in the middle, what you call as intrinsic level. This is the conduction band, this is the valence band, this is 1.12 electron volt at 300 Kelvin temperature. What is the Fermi level related to the bottom of the conduction band? Assuming this and this, you know that Fermi level exactly is at the middle. That means this particular thing is going to be equal to this particular thing. That means divided by 2, you get 0.56 electron volts. So this is the answer of this question. Oh, not above. No, it's 0.56 electron volts below the conduction band. If the Fermi level would be above conduction band, then it is a metal. It's not a semiconductor. That's a different story. Because for the metal, Fermi level is in the conduction band itself, and there is, I should say, there are huge number of electrons present near the Fermi level. That's why metals are highly conductive in nature. But here, there is a gap between the conduction band and the Fermi level, and the more Fermi level goes towards the conduction band, you know that the more kind of n-type it becomes, and more kind of, I should say, more number of electrons are easily accessible for the conduction. And now if it happens that Fermi level just crosses it and Fermi level comes here, it is as if it is metal, because now the Fermi level is in the conduction band. There are so many electrons accessible to the conduction band that they will be able to play the part in conduction easily, and it behaves as if it's a metal. And that is the story. Okay, so now question number 4. Consider an n-type semiconductor, and what's the time? Consider an n-type semiconductor where what is the Fermi level position related to the conduction band edge? Assume this Nc is equivalent to uh, Nc equals to this thing, and Ni is this thing, and D is this thing. Okay, so you have N-type silicon at 300, and you know that if it's N-type, the Fermi level will be somewhere near to conduction band. That's what professor might have covered. If the Fermi level is somewhere near to the valence band, it is more of a p-type. And what you have to do is that you have to compute the Fermi level position related to the conduction band. That means you have to compute, oh sorry, Fermi level, yeah, Fermi level position related to the conduction band. So this is the intrinsic level, and this is the separation between these two particular levels. So if you compute EF minus EI, you have something like KT ln of ND divided by NI. You compute this thing, you get some value, let's say, and because you know that this particular thing is 0.56 electron volt, this particular thing is 0.56 electron volt. So whatever you get here, you subtract that from 0.56, and you get the difference, which is EC minus EF, and you will get 0.15 electron volt below the conduction band. Obviously, cannot be above. It can be above. It depends on the computation. If it is above, then it's still n-type, but it's more like a n plus, something called an n plus type, and it almost behaves like similar to that of metal. So the answer of this question is this, but this is the calculation how you do it. Now question number 5. Okay, so question number 5 says that if you consider a Fermi-Dirac distribution at different temperatures, which of the following is true about T1 and T2? Now, if you talk about uh, this is the Fermi distribution at T equals to 0 Kelvin, it's a perfect step. That means this is Fermi level. That means above Fermi level, there is zero probability of electron to be found. Below Fermi level, the probability is maximum 1. This is 1 here. This is at T equals to 0 Kelvin. But the scenario at T greater than 0 Kelvin changes. As you go higher and higher in temperature, the Fermi function smears out. It kind of changes like this. It kind of changes like this. Where this particular temperature, as you increase the temperature, more and more probability of the electron becomes more to go to the higher levels of energy. Okay, so the probability of electron increases to go to higher energy, and that means the T2, what should be the relation between T2 and T1? It should be that T2 should be greater than T1, because as you increase the temperature, there will be more and more probability of electron to go to the higher energy states. And you can simply think about this Fermi function. Just put, if you put, let's say, T tends to infinity, you get f of e equals to 1 by e to the power, this is e minus ef by infinity. That would be 1 divided by 1 plus 1 by infinity is 0, e to the power 0. So you get 1 divided by 1 by 1, 1 plus 1, you get 1 by 2, you get the Fermi function as 1 by 2. That means it's almost as if the electrons have they are having the 50% probability of being at the Fermi level. That is what even is the definition of the Fermi level. You guys might be knowing about it. So, and if you let's say put T equals to 0 here at lower temperature, you get infinity, e to the power infinity, and you get 0. That means there are no electrons above the Fermi level. And you can just play with the temperature and the energies of this equation in order to check which fits here. But simplest explanation is, as you increase the temperature, more and more electrons want to go to the higher energy state, and there is a probability that more electrons will go to the higher energy state. So this is the probability function versus energy. Okay, so the correct answer of this is this particular thing. Now, if you have an intrinsic semiconductor where the intrinsic carrier concentrations are given, There is a relation that intrinsic concentration square is equivalent to square root of NC e to the power minus Eg divided by kT. This professor might have talked about maybe, but this is a simple relation which comes from the solving the density of states, considering the Boltzmann relation for the energy, and from this relation you see that Ni is proportional to e to the power minus Eg divided by kT, or ln of Ni is proportional to negative of Eg divided by kT. And if you just think about it, it is just like a straight line. These are straight lines, but negative slopes, where the slope is this thing. It is just like y equals to mx plus c. M is the slope, c is the intercept. Remove this intercept for time being. So y is ln of ni equals to x is 1 by t because they have plotted against t. So it's 1 by t is x and the slope is minus eg over k. That means it's having negative slope. These all are having negative slopes. This and this. And what is happening is that as you go on increasing the temperature is increasing in this direction. Because if you increase the temperature, thousand over increasing the temperature, thousand over T will reduce. Okay, so the temperature is increasing in this direction. So what is happening is that if you go on increasing the temperature, what is happening to the slopes of these? You see that this particular slope, let's say slope 1 is this is slope 2, this is slope 3. You see that the slope of 3 is greater than slope of 2 is greater than slope of 1. And the slope is actually this particular factor here, band gap. That means Eg of 3 is greater than Eg of 2 is greater than Eg of 1. That is the answer of this question. Eg of 3, let's say Eg of 3 is, okay, so this particular thing. Yeah. And the simplest explanation can again be that if you go on increasing the temperature basically changes the band gap. And if the band gap reduces, let's say this is Eg1 and this is Eg2. So if the band gap reduces from this to this, there is more chance of electrons to go from this region to this region. So there will be more kind of intrinsic concentration generated in this region as the band gap is reduced, because the band gap is having the relation with temperature as some kind of this relation, where if you increase the temperature, the band gap reduces. In case of silicon, in case of silicon semiconductor.
Sir, someone will argue that the temperature change cannot affect the band gap except Fermi level position. Is it?
Huh, that explanation can also be given, or even the simplest explanation is in terms of this equation. If you kind of see just the slopes of these, the slope of these is changing. This one is having more slope than this, and you can simply tell that this one is having more Eg, less Eg, the lesser Eg. That means if this is like this scenario, then energy gaps are different. Then you will see simply at particular, let's say this point, these are having different Ni concentrations at the same temperature. That's what your argument is. At same temperature, this is N1, N2, N3. These are different concentrations. Why? Because the band gap values are different depending on the slopes of these lines. All right, you got it.
Yes, sir.
Now that is the simplest. I mean, you can explain it by keeping the temperature constant. You can explain a curve in a million ways. It just depends upon whether you are kind of it is right as per the physical laws. Okay, so another questions. Uh, maybe this is the last question because now I'm kind of feeling a little bit exhausted because I will be putting the other two questions. Maybe there are eight, nine, and 10 questions. I think they are
So,
quite
sir,
kind
in
of
that case, if band structure, everything will changes. at the temperature dependent, like, so there will be temperature dependent band structure will also be possible.
Right, right, right. But that means, because what temperature does is that these are the atoms. Okay, you notice that when I draw this potential in the first slide, oh, when I draw this potential in the first slide, I considered these atoms to be static. That means they were not moving at all. But that's not the case. These atoms kind of vibrate, and what increases the vibration is temperature. And this particular lattice constant is also changed by the temperature. It is as if you just increase the temperature so much so that solid gets converted to liquid. In the solid, atoms were close. In liquid, atoms become farther apart. In gases, atoms are very far apart. So temperature changes the lattice spacing also, and that reflects in the variation of the band structure as well as the energy gap. You got it?
Yes, sir.
Okay. So and and this particular thing, what you call as band diagram, this is E versus X, E versus space. This this schematic actually comes from band structure, because if you consider the band structures like this, where this is the conduction valence band, this is the conduction band, you only treat this particular region and you draw it here in the EX, E versus X. That is what the band diagram is. That means in the band diagram, if you have band diagram like this, EC, EV, you have X here, you have E here. But at every location, there are these parabolas. But these parabolas are like this region of the parabola, this region, ये वाला region. ठीक है? तो ये एक्चुअल में एक्सट्रापोलेट करके हम बैंड डायग्राम पे दिखाते हैं. तो इसीलिए इफ यू रिमेंबर, मैंने इसको पैराबोला से अप्रोक्सीमेट किया था ऐसे, बिकॉज क्योंकि हम मोस्ट ऑफ द टाइम इन स्टेट से कंडक्शन करवाते हैं, मतलब ये हमारे इंपॉर्टेंट स्टेट्स होते हैं यहाँ पे, which take place in conduction mostly. We don't mostly talk about these higher states, these ones. Maybe in certain cases, but to the first order approximation, we talk about the states which lie at the bottom of the conduction band and at the top of the valence band. That are the states, those are the states which are very important to us. And those are shown in the band diagram here. Okay. So that is ये सीधे बैंड स्ट्रक्चर से ही हम ये पर्टिकुलर थिंग एक्सट्रापोलेट करते हैं. Okay, so now this question I'll discuss again. This is the same question. You know that ni square is proportional to e to the power minus eg divided by kt. But let's say remove this square here. इसके बदले हम 2 लिखते हैं यहाँ पे. And what you have, uh, okay, so this is the ni concentration. This is talking about two non-degenerate semiconductors. Non-degenerate means the Fermi level is far below that of the conduction band. Ec minus Ef is much greater than Kt. This is the non-degenerate semiconductor. If you have very close Ec and Ef, if Ec minus Ef is approximately Kt, or some people say 3 Kt, this is called a degenerate semiconductor. Now he is talking about the non-degenerate semiconductor. The band gaps are EGA1, EGA2. The respective resistivities of these two materials with the reciprocal temperature. It's the same plot, except he has plotted resistivity, log of resistivity, and this is log of this is 1 by temperature. So you know that conductivity is the charge times the number of electrons times the charge times the mobility. You can write the conductivity as 1 by resistivity. It's equal to n e mu, where this n is here the intrinsic concentration, this concentration. That means if you consider these to be as constants, let's say that means Ni is inversely proportional to resistivity. इसका मतलब ये हुआ कि if Ni increases, resistivity will reduce. A simple explanation because the conductivity increases. Now you do the opposite thing as that of the previous question here. You write that this is ln of Ni is directly proportional to minus Eg divided by 2 kT, and because if Eg increases, Ni will reduce. If Eg reduces, Ni will increase. That means इसका जो स्लोप है वो उल्टा होगा पीछे वाले एग्जांपल से, because this time resistivity, and resistivity is inversely proportional to 1 by Ni. Okay, so this time the particular slopes will be opposite to that of the previous question. Now if this is Eg1, this is Eg2, then you know that if this is more slope, this is less slope, that means Eg2 is greater than Eg1, and it means that conductivity, Ni, oh, it's not Ni, resistivity. If the Eg2 is greater than Eg1, that means the answer of this question is, where is it? EGB is greater than EGA. I hope that's the answer of this question. Because this time it is the resistivity plot versus the 1 by temperature plot. And if you have something like Ni is directly proportional to e to the power minus Eg divided by 2 kT, you bring exponential on this side, you write it as ln of Ni is directly proportional to minus Eg divided by 2 kT. And you write it as ln of Ni, let's say, is equivalent to Eg by 2 k 1 by t. What you plot is this versus this. When you plot something where one of the axis, y-axis, is in log scale, this particular plot is called as semi-log plot. Semi-log plot. Because here this is not in log, this is in linear scale. But this particular scale is in log scale. It's a semi-log plot. So you have to consider it. Sometimes mathematically people get confused by this terminology, semi-log plots, or where this axis is shown in log, this is in linear. Or sometimes this is in log and this is in linear. So you have to interchange it. And accordingly, you can apply the straight line equation to this. You find this is the slope, this is the x-axis, this is the y-axis. And you can write, that Ni is inversely proportional to rho. So whatever is the case with Ni, uska ulta rho hoga, and that will give you the band gaps as particular these values. Or in other words, if the band gap increases, Ni will reduce. Ni will reduce, that means resistivity will increase. Simple. The material become more resistive. Just like if you have silicon, 1.12 electron volt. If the band gap increases to 9 electron volt, it will become resistive. This will become an insulator. And this is the band gap of silicon dioxide. It will become insulator. That means it will resist the flow of current. Simple. Okay, let's leave question 8, 9, and 10 to the I will explain them in the other session or in the video, because this session is now getting longer. I don't know. Uh,
Sir, a last question. Can I ask?
yeah, yeah, yeah.
Yes. Thank you, sir. Sir, so these band structure and like continuous bands, and this is for crystal case, like right. So someone will like write homo-LUMO concept for molecular cases.
That is the same thing. If you have,
Uh,
see, these are not, uh, Basically, you have a good doubt. That is the doubt most of the students have. When you let me not draw this. Let me take just a conduction band here, a valence band here. This particular bottom is a valence band. This particular thing is a conduction band. And this is the first Brillouin zone. Minus pi by a to plus pi by a. This is k. Alright, and this overall thing is 2 pi by a. So when I told you that this particular thing is having, it's this particular thing is not even continuous. It is actually a discrete states here for the electrons. But they are so closely spaced that it appears to be as a continuous. These are not even continuous states. Why it's not continuous? Because when I talked about going from a real lattice to the reciprocal lattice, यहाँ पे ये जो डिस्टेंस थी a है और ओवरऑल क्रिस्टल का डायमेंशन l था, लेकिन अभी यहाँ जो ये डिस्टेंस है वो l है और ये जो डिस्टेंस है वो a है. तो what happens is that because of their going from real space to the Fourier space, ये डिस्क्रीटाइज स्पेसेस है यहाँ पे, इन दो स्पेसेस के बिटवीन जो डिस्टेंस है वो 2 पाई बाय एल है एक्चुअली, और आई शुड से पाई बाय एल है हर एक स्पेस के बिटवीन यहाँ पे. So that is a very, I should say, a very smaller number as compared to that of these discrete states are so closely spaced on this particular curve that they appear to be almost continuous. And what happens is that now if you kind of take this similar concept of conduction band in the valence band, and if you go into the molecular picture, if you have molecules, basically two atoms, that's a molecule. If you combine two hydrogen atoms, you get a H2 molecule. And you get basically, let's say इसका ये पोटेंशियल था और इसका ये पोटेंशियल है, तो इसकी एनर्जी लेवल ऐसे थी, मतलब ये इसका एनर्जी लेवल था जहां पे इलेक्ट्रॉन रिजाइड कर रहा था, ये इसका एनर्जी लेवल था जहां पे इलेक्ट्रॉन रिजाइड कर रहा था. नाउ वी हैव brought them closer, we have made a molecule. What happens is that these energy bands, both of these energy redistribute, and they form something called as bonding and anti-bonding energy level, or sometimes you call them highest unoccupied molecular orbital, lowest, what are they called? I don't remember the terminology. Homo and lumo. I think this is highest occupied molecular orbital, lowest unoccupied molecular orbital. That means this
Yes,
particular
yes,
electron,
Homo Lumo.
these two particular electrons reside here. ये both यहाँ पे आ जाते हैं with upspin and
Yes,
downspin,
yes,
and
yes.
ये खाली रह जाता है. That means इसीलिए lowest unoccupied, ये खाली है. It is a similar terminology कि if you have a band where there is a structure like this, you can, because all of the electrons are here and this particular band is empty. This is empty. This is because it's a conduction band. This is a valence band. You can call this LUMO. You can call this HOMO. It is same thing. It doesn't matter. So that is the same thing what happens here. Now you have combined two molecules. You go on combining many. You have combined two atoms. You get a molecule. Now you go on combining many of the
But if I
atoms.
have a group of molecules which molecular interactions are weak and only intramolecular attractions are there,
Hmm.
then they will only like having only two, the significant transitions are only for two levels, right, sir? All are
Hmm.
like
Right.
identical
So
structures.
that is what, if you go from two atoms to many atoms, when you go to many atoms, that is what the solid picture is. That is the solid picture. You get these energy levels as these bands. ओके, सो क्या होता है कि अब यहाँ पे अगर सॉलिड पिक्चर में दिखाए सिमिलर जैसे हमने हाइड्रोजन एटम में दिखाया, तो ये अगर पोटेंशियल्स है फेस्ड बाय द इलेक्ट्रॉन्स, यू गेट यहाँ पे एनर्जी लेवल है अपनी जो अलग अलग डिस्क्रिटाइज एटम की एनर्जी लेवल थी, तो यू गो हायर एंड हायर तो जितना जितना हायर जाओगे, एक्चुअली आई शुड शो दीज एटम्स हियर, एटम्स यहाँ पे है। तो ये जो ये ब्लैक है, ये यू ऑफ आर है, ये आर है, स्पेस कोऑर्डिनेट। तो एज यू गो हायर एंड हायर, देयर आर एनर्जी स्टेट्स, एंड एज यू गो बहुत ज्यादा हायर, देयर इज अ कंटिन्यूअस बैंड ऑफ एनर्जी इज प्रेजेंट। So this is such so continuous that it almost appears like a band. ये जो डिस्क्रिटाइजेशन है अलग अलग लेवल्स में वो खत्म हो जाती है, यहीं पे डिस्क्रिटाइजेशन रह जाती है, इसीलिए ये इनर स्टेट्स है। और ये एक्सटर्नल, मतलब नॉट एक्सटर्नल स्टेट, दीज आर द स्टेट्स विच आर ऑलमोस्ट लाइक द बैंड्स, दे आर वेरी फार अवे फ्रॉम द न्यूक्लियस, वेरी फार अवे फ्रॉम द न्यूक्लियस। इसीलिए अगर यहाँ पे कोई इलेक्ट्रॉन होता है तो दैट मूव्स एज समथिंग कॉल्ड एज नियरली फ्री इलेक्ट्रॉन, that moves like a plane wave. इसीलिए I considered plane wave in the second explanation of how the band structure arises. When we talk about the plane wave, you talk about e to the power minus I kx, because electron here moves like a plane wave. अगर इलेक्ट्रॉन को मैं यहाँ कंसिडर करता तो यहाँ इलेक्ट्रॉन एक पोटेंशियल वेल में है, ये प्लेन वेव नहीं है, और इसका जो सोल्यूशन है वो श्रोडिंगर इक्वेशन वेव फंक्शन देता है। ये भी एक वेव फंक्शन है, बट ये प्लेन वेव फंक्शन है, प्लेन वेव फंक्शन है, बट यहाँ जो सोल्यूशन होगा इलेक्ट्रॉन का वो डिफरेंट है। वो वो सोल्यूशन कुछ अलग वैल्यू देगा, मे बी वो ऐसा देगा वैल्यू, ये वेव फंक्शन होगा इलेक्ट्रॉन का, साइन ऑफ के एक्स विल बी द वेव फंक्शन ऑफ इलेक्ट्रॉन, जस्ट लाइक इन अ पोटेंशियल वेल। सिमिलरली यहाँ पे अगर इलेक्ट्रॉन होगा, बट जैसे जैसे इलेक्ट्रॉन की एनर्जी ऊपर जाती है, इलेक्ट्रॉन ऊपर जा रहा है एनर्जी लेवल्स में, ऊपर इतनी सारी एनर्जी लेवल्स है दैट इट इज ऑलमोस्ट लाइक अ बैंड, एंड इलेक्ट्रॉन फ्लोज freely, nearly freely. That is actually the case in metals mostly.
So, but if this is possible for like molecules, if they become crystallized, and this then
Yes,
this hybrid structure will form.
yes,
If the
yes.
molecules are like inert and they are like a like organic molecules in solution, they will be just like single molecule. They won't become crystallized. For them,
Hmm.
like this won't work, right? Or
Right,
will it?
correct. That's why this particular scenario is only applicable to crystalline. That means periodicity.
Okay.
अगर periodicity नहीं हुई तो जो ब्लॉक की थ्योरम है वही गलत हो जा रही है। तब जाके यू कैन नॉट से कि तुम पोटेंशियल को यहाँ थोड़ा सा लोगे तो वो सेम होगा यहाँ का पोटेंशियल, नहीं। अगर पीरियडिसिटी नहीं हुआ, मतलब अगर एक एटम यहाँ पे, दूसरा यहाँ, तीसरा यहाँ, यहाँ पे ऐसे रैंडम रैंडम ऑर्डर ऑफ एटम्स है, जो कि एक ऑर्गेनिक मॉलिक्यूल्स में होता है, ऑर्गेनिक इसमें होता है, राइट।
Yes,
दे
yes.
आर दे आर मोस्टली काइंड ऑफ एमरफस। तो वहां पे
Okay.
क्या होगा कि पोटेंशियल प्रोफाइल ऐसे होगा कुछ, ऐसे, 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 एंड दिस इज काइंड ऑफ बिजार थिंग। यू कैन नॉट से देखिए इलेक्ट्रॉन यहाँ जो फील कर रहा है वो यहाँ फील कर रहा है, रॉन्ग। यू कैन नॉट अप्लाई ब्लॉक्स थ्योरम डायरेक्टली यहाँ पे। यहाँ पे क्या होता है वो डिफरेंट सिनेरियो, दैट इज मोर कॉम्प्लेक्स देन द क्रिस्टलाइन, बट इट इज अ वेरी काइंड ऑफ, आई शुड से, एक्टिव रिसर्च एरिया अभी भी है। इस पे लोग रिसर्च करते हैं कि इलेक्ट्रॉन को ऐसे रीजन्स में कैसे हम स्टडी करें जो कि क्रिस्टलाइन नहीं है,
Um,
बट इट्स मोर कॉम्प्लेक्स देन दैट ऑफ द क्रिस्टलाइन।
So the
ओके,
theoretical condensed matter is fully dealt on these kind of hybrid structure studies. The
which
structure
which
are
which which condense matter?
like theoretical condensed matter physicists, they will only
Yes.
deal with this.
Theoretical condense matter, yes, deals with the periodic structure, but nowadays they also deal with this thing, amorphous,
Okay.
using certain techniques like density functional theory, and these are very kind of complicated things. Density functional theory, or basically you have to consider many interactions here. It's not a simple
Um,
picture. So that's a different scenario.
okay.
Okay, so this session has, I don't know, gone very long. So I think, does anybody have any other question? If so, then I have to charge my pad first because it's getting almost from 70% to 23.
Sir,
Yes.
16 conception is abstract.
Sorry? Say it again.
Scheme conception is abstracted.
I don't get you what you are saying. If anybody else is able to get him, then let me know. I'm not able to hear you properly. Can you just
He's
say it
not
again and
speaking,
louder?
sir. I think he left.
Okay, he left. Okay. Did you understood his question? Or were you able to
No,
understand
sir.
his question?
No, his voice is very
Okay,
disturbing,
so
like noisy.
okay, so any if you have any other question, then you can just tell me. Otherwise, I'll be stopping this meeting at exactly at 20:45. That means 8:45.
Yes, sir, you can talk. Thank you, sir. It's very brief explanation.
Thank you.
This video will be uploaded, right, sir? So I can repeat it.
Yeah, yeah, yeah. I'll be uploading this video definitely. It'll be a longer video, but I'll upload it.
Thank you.
Okay. Thank you. All right. So I am ending this meeting here. Thank you, guys. See you next week.